All right, welcome back. Hopefully you all survived the WPR. We're moving on to a new block. This one is on rotational dynamics. And for this lesson, the introduction to rotation, I chose to do text problem 10-23. All right, so at this time, if you haven't already, pull out a blank sheet of paper, some scratch paper, or a blank copy of this problem from the SharePoint site, because I'll be pausing periodically to have you work through the problem or a portion of the problem on your own. All right, so as we get into this problem, we have first our read step, and we can see that we have some important aspects of our rotating disc here, our flywheel. We have a diameter, we know what its angular speed is, and the rest of the given information will come out through parts A through D. So I can see that when I want to find my angular speed in radians per second, I'll need to do some conversions, but from this I can see that I have definitely some rotation, and I'm going to go with kinematics. You might be thinking, but how can we do kinematics on a problem that is spinning in circles? Well, it's rotational kinematics, and you'll see how they actually line up almost exactly with what we've been working on up to this point. All right, our next step, we're looking at the draw step, so give me a moment to draw and I'll be right back. All right, so here is our flywheel in black, and I have my dimensions here in red. I want to point out something new. So I have my X and Y coordinates, but notice how I've also written in this arrow that points clockwise and has a plus here inside of my little arrow. You can either put it inside or outside, whatever you feel familiar with, but that is to let the reader know that anything spinning clockwise is in the positive direction. This is going to be important when we start to talk about angular velocity and angular acceleration, because the direction of those vectors will follow the right-hand rule, which I will get into once we start pulling out some information. Okay, so draw step complete. Move on to our givens. All right, here are our givens. I took my diameter here of 1.2 meters, divided in half, so I have 0.6 meters as my radius. I wrote down my two angular speeds, 200 revolutions per minute, not per meter, and 1,000 revolutions per minute, which will come up in part C and, part C. And then the time it takes to go from 200 revolutions per minute to 1,000 revolutions per minute. And of course, there's going to be some acceleration there, like we see in part C. All right. Assumptions. What assumptions might we make? Well, what assumption did we make when we did regular Cartesian kinematics, i.e. stuff in the X and Y direction? Well, we said no air resistance, right? Well, we have to assume the same thing. We're assuming that we have a constant acceleration. Except we're rotating, so our acceleration is going to be angular in nature. All right, so with that in play, we can now move on to our tasks. Part A, calc omega in terms of radians per second, because that's how we report any type of angular motion, is in radians per second, or radians per second squared. And I'm going to pause and delve these out. All right, so the rest of our tasks, we're going to calculate the tangential velocity at the rim. So I have at radius r. Part C is to calculate the angular acceleration, and then Part D, how many revolutions does it take for our accelerating flywheel to go during 60 seconds. So we're going to calculate the angle, and we're going to do that in terms of revolutions, so we'll have to do some conversions from radians to revolutions. All right, and then we go to the physics step. I want you to pause the video, write out the physics equations you think you'll need. Think rotational kinematics. Should be pretty easy to find on the PRC. Once you've written those out, resume the video and we'll meet back up. All right, so as we come back, hopefully you have some similarly looking equations here. I wrote down all three kinematics equations for our rotational kinematics. And notice how eerily similar these look to the translational kinematics. We have our relationship between a final speed and an original speed given an acceleration and amount of time. We have our angular displacement given an initial angular speed, the time, and the acceleration. Then we have the relationship between the angular speed, the final angular speed, the original angular speed, and the acceleration and displacement. So these should all look pretty familiar. We've just changed the nature of the motion from translational to rotational. Now I've added one link equation. It's right there on your PRC that connects the translational and the rotational. And so this V speed right here, it represents the tangential speed or the linear speed that we see in the problem. So that is going to be dependent on not just the angular speed of how fast it's rotating, but where on the disk we're looking at that tangential speed. So that's where the radius variable comes from. All right, so let's get to work. All right, so for part A, what is the angular speed of the flywheel in radians per second? So we're given 200 revolutions per minute. And we need to get to radians per second. So we have to convert both the units on the top and the bottom. From chemistry, you should recognize the picket fence. So in one revolution, we have 2 pi radians. And in 1 minute, we have 60 seconds. All right, so as we look at our values here, our revolutions should cancel, our minutes should cancel, so we're left with radians per second. So the result is omega in terms of radians per second is 20.9 radians per second. All right, so let's move on to part B. Part A, part B. It asks us to find the linear speed of a point on the rim of the flywheel. So as I mentioned, we have those link equations on the PRC. They relate the translational piece to the rotational piece. So in this part of the problem, we want the tangential speed at the rim. And we work in radians per second because they are essentially, radians are more or less unitless. And now we can work through, we know that our radius is half of the diameter like I put in the givens. So 20.9 radians per second times 0.600 meters. And we have 12.6 meters per second. I know it can be confusing sometimes because we have radians here in our intermediate step, but when we get down to the final solution, they're gone. Again, radians, they signify an angle or an angular displacement, but when it comes to actually capturing them in actual arithmetic, they can disappear. And that's why we use radians in our trig terms, because inside of our trig argument it needs to be unitless. So that's what radians are. Okay, so as we move into part C, we need to calculate the angular acceleration going from an initial angular speed to a final angular speed. So do a quick kinematics table. I want you to pause the video, fill out your kinematics table, but in terms of your rotational variables, and we'll see which equation we need to use to continue. All right, so here's my kinematics table. I have my initial angular position. I have my final angular position. I have my initial angular speed, my final angular speed, and my angular acceleration with a elapsed time, in this case, is 60 seconds. So like usual with any kinematics problem, we often assume that our initial position is 0, so that's what I've done with this problem. I don't know where I'm ending up after these 60 seconds. I think we'll find out in part D. And here I have my initial and my final, and we need to find this angular acceleration. So looking at my kinematics table, I see that my first kinematics equation is going to be the one I need, which is the angular speed in the final frame is equal to the initial angular speed plus the angular acceleration times the elapsed time. All right, so I have the first two. I have this variable, and the time. So all I have to do is solve for the angular acceleration. All right, and we get 800 revolutions per minute squared. Now I'm going to take a second here, and give me a second to drop another flywheel on. All right, so I have my flywheel here. I said it's spinning clockwise. Notice that my angular acceleration is positive. But what if my final angular speed was smaller than my initial angular speed? Well, I have a smaller quantity subtracted from a larger quantity. I'd end up with a negative answer. Okay, well, we learned in translational kinematics that if my acceleration and my velocity had opposite signs, i.e. the acceleration was pointing in the negative x direction and the velocity was pointing in the positive x direction, then that meant I was decelerating. If my velocity was in the negative x direction and my acceleration was in the positive x direction, I was still decelerating. Well, we see the same thing with rotational kinematics. The difference is the direction that the vector points. So in rotational kinematics, first we declare the positive direction for motion. And if you remember on the previous slide, I said that my positive direction was pointing clockwise. That means that we're going to use the right-hand rule to let us know which direction the vector is pointing. All right, lastly, part D. Well, hopefully my movie within a movie didn't break your computer or break anything else. But as we sit, part D, how many revolutions does the wheel make during those 60 seconds of angular acceleration? Well, we can go back to our kinematics table, and we can now use the information we got from part C, which was finding this angular acceleration. and try to drive out how many rotations occurred or how many revolutions occurred. So given this information, we need to find our final angular position. Given our initial angular position, we will then be able to find out the angular displacement, or how many revolutions occurred during our 60 seconds. So this is going to be our equation we need to use, because we need to find our final angular position. And it's going to be, because of our units here with revolutions per minute, it's going to be in terms of revolutions. Alright, so besides having to make a quick conversion of our 60 seconds into minutes, which should be pretty snappy for us all, we will get our angular displacement. So we have our initial angular speed of 200 revolutions per minute times our 60 seconds, or 1 minute, plus 1/2 of our angular acceleration times the total time elapsed of 1 minute squared. And the answer we get is 600. Put a dot there for 3 sig figs, and that's total revolutions. And that completes this text problem. I hope that you come ready and eager to learn as we get into some pretty fun stuff with respect to rotation. I'm just going to say, as a forewarning, prepare to get dizzy.